This video will demonstrate how to use static to conduct a one-way analysis of variance. And to illustrate this example, I'm going to use the flipped classroom data. And the goal here is to compare students' scores under three different teaching conditions. And so we'll look at Classroom 1 that uses instructional videos, Classroom 2 that uses videos and discussion, and Classroom 3 that uses videos and group performance assessment together. And so the goal here is to determine if these students differ significantly on their test scores in the use of these three different methods. And so what we'll do is we'll open our data in Stata. So we have our flipped classroom data here. And then we'll browse that data a little bit. And what I've done is I've abbreviated. So I have teaching method as divided into instructional videos, videos and discussion, and videos and group performance assessments. And so the dependent variable for each student under these three different conditions is their test score. And so to conduct the one-way analysis of variance, the first thing we want to do is kind of check the assumptions. So let's just look at the histograms of these scores by these three different groups. So we can select score. The data are continuous, and we want to do this by subgroups. So our subgroups are groups within teaching method: instructional videos, videos and discussion, and videos and group performance assessment. And so we can submit that, and then we can take a look at our three graphs. And so because we don't have a lot of scores or a lot of students in each group, we can see our data looks a little bit skewed. So it's skewed in the positive direction here, and in this case we have a bimodal distribution. So what I'm going to do is save these graphs, and I'm just going to call them one-way ANOVA, or I could call them flipped classroom, and I'll save them to my desktop. Then I can look at them later. But what we really need to do is run our tests to determine exactly if these different groups are significantly non-normal. And so to do that, I can go up to Statistics, Summaries, and then I can go to Distributional Plots, and I'm going to go to the Shapiro-Wilks normality test. And so I want to use my dependent variable score, and then I want to do it by each test. So, or by each group, I'm sorry. So I want to be able to test the normality for each of the three different groups. And so I can go OK, and then in my output I can see that the Shapiro-Wilks test for instructional videos is not significant, so we don't have a situation where we have significant non-normality. Video and discussion is not significant, nor is video and group performance assessment. So our data is basically normal. It's not significantly non-normal. Now, the other assumption that we like to look at, or we need to consider, is, are the variances for these three groups similar? And so if we look at our descriptive statistics, we can look at score, and then we can divide that the means and the standard deviations out by teaching methods. And so here's our mean and standard deviation for instructional videos, our mean and standard deviation for videos and discussions, and our mean and standard deviation for videos and group performance assessment. And so these standard deviations look pretty similar, but we're going to go ahead and run a test to just determine if they differ significantly from one another. So we'll go ahead and go to classical tests and of hypotheses, and then go to, in this case, we're going to use robust equal variance test. And so our variable that we're looking at to see if the variances are equal is score, and our grouping variable is teaching method. And so we'll go ahead and, let's see, I don't think I need to do that. No, cancel. We'll go ahead. Oops, I canceled it. Let me start that over again. And we'll put teaching methods here, and then we'll submit. And so we can see that our first variance does not differ significantly from the second and third variances. And for group 2, our variances do not significantly differ from the other 2 variances, as well as group 3. These variances do not differ significantly from one another. So we can see that we've satisfied that equality of variance assumption between these 3 groups. And of course you can just eyeball and see that these standard deviations are very similar to one another. So we can go back up to statistics. We'll go to linear models this time to do the ANOVA, and then we'll go to one-way ANOVA. And our response variable this time is score, and our factor variable is teaching method. And then what we need to do is check one of our multiple comparison tests. And these multiple comparison tests are the same as what you may have read about in terms of what's called a post hoc test. Because if the ANOVA is significant, then we want to know how teaching methods differ, which students perform better under different teaching methods than other students. And one of the ways that we do that is by comparing those means after the ANOVA has been conducted. So we can just choose one. We're going to choose the Bonferroni multiple comparison test, and then I'm going to produce a summary table. And so then we can go OK. So now what we have here is the summary table provides us with the means for each group and the standard deviations, and then the grand mean. And in our analysis of variance summary table, we have our between group sum of squares, our within group sum of squares, and our total sums of squares. These are the degrees of freedom between groups. That's k minus 1, so 3 groups minus 1 is 2. And within groups, there's 30 students minus 3 groups is 27. And then our total number of degrees of freedom, which of course add up here, is the n minus 1. So 30 minus 1 is 29. This is our mean square. So this is the average variability between groups. So 2 divided into 2240 yields 1120. And then 27 divided into 6280 yields 232.59. So if you divide those using your calculator, you'll get these results. And then the F ratio is simply this ratio here, 232.592 divided into 1120, and that's your F ratio, 4.82. So STAT calculates the probability. So the probability that at least one group differs from another group is 0.01. So that's certainly less than 0.05. So our result, our ANOVA, is significant. And we had the Bartlett's test here for equal variances, and we did see that already. We did test that, but this again confirms that our Bartlett's test for equality of variances is non-significant. So this is definitely greater than 0.05. So then we have our multiple comparison test. So what this does is it compares all or makes all possible comparisons. So video discussion compared to instructional videos. So this mean compared to this mean, the difference is approximately 4. This is rounded off. And this is the probability of significance. And so we can see that this is not a significant result because it's certainly greater than 0.05. However, if we look at the difference between video GPA and instructional videos, we can see that that difference is 20. So let's see, where is that? So the mean for GPA compared to the mean for instructional videos. So instructional videos, so videos and group performance assessments minus instructional videos is 20. So the average difference is 20, and so this is significant. This difference is significant. So what this says is that video and group performance assessment, these students perform significantly higher than students that just had the instructional videos. And then we can see videos and group performance assessment compared to videos and discussion. So if we compare this mean to this mean, the average difference is 16, and that result again is not significant. 0.08 is certainly greater than 0.05. So what we see here is that videos and GPA are significantly higher. Those students have a significantly higher mean score than students with instructional videos, but there's not a significant difference between videos and GPA and students with videos and discussions. So I hope this explanation of how to do a one-way ANOVA using STATA helps.